Most rural and urban buildings from the Dark Ages right through to the late 17th century were built in timber. Many survive today, and they're an important part of our architectural legacy. This 15th century terrace in Tewkesbury shows typical construction of the late medieval period. Built by the local abbot as a speculative development, the terrace is a stylistically simple, yet at the same time technically sophisticated example of this traditional craft. Surviving timber buildings tend to be of high status and are increasingly rare. Nearly all of them are protected by conservation legislation, primarily through their inclusion on a list of protected buildings, hence the term listed building. The extent of conservation work and the repair techniques should be informed by a set of guiding principles, which in the main seek to limit the destruction of historic material. Both policy and attitudes towards the treatment of historic buildings have changed over time. In the past, preservationists sought to return a building to its original form, which often meant removing later alterations and additions. Changing the original nature and use of a historic building was not acceptable. Nowadays, conservation takes a more pragmatic view. Change is acceptable as long as it doesn't damage the cultural and historical significance embodied in the building's fabric. Before we can consider the repair options, we need to know how these buildings were constructed and how they deteriorate.
Welcome to the Open Air Museum at Singleton. We've got here a timber frame that's been made by students on a number of different courses. The timber frame illustrates all the basic timber components and the joints that are used to connect them together. The first timber we come to is the tie beam. This timber is in tension and it basically stops the building from spreading apart. The tie beam is connected both to the wall plate and to the principal post. The wall plate is supported by studs at the mid-span, picks up the loads from the rafters and transmits them through the studs and through the principal posts down to the sole plate. In order to stop the building racking or moving from side to side, the wall plate and the bay post are connected by braces using mortise and tenon joints. The braces resist these movements by working in compression, and the forces are obviously transmitted through the shoulders of the joints. And it's these joints which are critical to the structural success or failure of the building.
The integrity of the frame depends on its joints. Some are quite simple, others are much more complex. The mortise and tenon is by far the most common. It consists of a squared hole in one timber, a mortise, and a tenon at the end of the other. The mortise and tenon are fixed together by timber pegs. Where the roof meets the wall, complex loads are created. The joint assembly reflects this. The post is thickened or jowled, providing sufficient timber to enable a durable connection with the other components. The wall plate is attached to the post using a pegged mortise and tenon joint. The wall plate tends to rotate because of the thrust from the rafters, and to lessen this effect, the plate is captured by jointing the tie beam to both the plate and the post. The principal rafter is also jointed to the tie beam. This assembly is unique to the UK's tradition of timber framing. When erecting a timber frame, the first and most critical activity was to set out and level the sole plates on a low plinth wall. The various components of this prefabricated system were pre-cut and test-assembled in a carpenter's yard. The frame was then taken apart and transported to site for raising. The individual timbers and part-assembled bays were probably raised in sequence by a team of carpenters using ropes and shear legs. A marking system, often based on Roman numerals and cut into the components, enabled the carpenters to identify the precise location of each timber.
The two main reasons for failure in a timber frame building are firstly water ingress and secondly structural movement. As most timber frame buildings were built prior to the introduction of damp-proof courses, the sole plate is particularly vulnerable as it's in direct contact with damp masonry. If the roof covering is also to fail, the wall plate, the bay post and the tie beam are also vulnerable where they're jointed together to water ingress and to decay of the actual joints themselves. Structural movement basically occurs because of foundation failure. Again, most timber frame buildings were built on very shallow foundations, and this has allowed the buildings to move over the years. As the timber frames move, the loadings on the individual joints change and in some cases can lead to failure.
There are a number of widely accepted conservation principles. These are not hard and fast rules, but they are generally regarded as sound guidance. There are 5 key principles: minimal intervention, like-for-like repair, reversibility, honesty, recording.
Minimum intervention, I suppose, is always the key because we are interested in the historic object. As long as we've made the decision that it is the historic object we're interested in preserving and not the craft process that gave rise to it, because those are 2 different objectives in conservation.
Minimal intervention can be applied to the analysis of a defect as well as its repair. Nowadays, non-destructive testing techniques allow the structure to be examined without causing too much damage to surface finishes.
While I would generally support the use of like-for-like materials, I'm not sure that it's right to say that you should always use approaches in conservation which are within the tool bag, if you like, of the traditional carpenter. As I've said, I'd like to think of people who work on the conservation of buildings as conservators, probably in addition to being carpenters. And you will have in your tool bag of techniques for conservation, techniques which are not necessarily part of the traditional carpenter's tool bag. So I think it's important to be clear that conservation is a different operation from the original craft itself. Reversibility is one to bear in mind. Certainly reversibility can be achieved with the use of superficial steel strapping of that kind of thing if it is structural problems you're trying to solve. But as soon as you make a cut into a timber, you have stopped being reversible because you can't uncut a cut. And I think that has given rise to a good deal of confusion over the years as to what actually is reversible and what is not. Honesty is a word that I try to avoid if possible, because not that I want to be dishonest, but I think there are more appropriate words expressing a similar idea. Legibility and discretion are two words which I think are preferable to the simple word honesty in respect of the repairs. I would say do not hide repairs in a conscious way, but at the same time I don't think it's right to let the appearance of the repair dominate the appearance of the repaired object. The crucial underlying thing that I think is important is understanding. It is absolutely essential to have a full understanding of the object that you're dealing with technically and historically before you start. And overall, you have to be clear what you're doing. Clarity of intent is important.
The last principle in building conservation is the importance of recording. This should include drawings, surveys and photographs of the existing fabric. Records should also include research material on the historical development of the building and a log of decisions made during the conservation process.
Once you have a full understanding of the problem and its cause and effect, you can then move on to considering the options for repair. There are 4 basic options for repair. The first is to do nothing, the second is a timber repair, thirdly a metal repair, and fourthly a resin repair. The option of doing nothing is often used where historic decay and or movement has been discovered, but the overall effect of the movement and decay doesn't structurally affect the integrity of the frame. Timber repairs are mainly used when we've lost part of the section of a timber or to replace a complete component. Metal repairs are often used where we have partial or full failure of the joints connecting the timbers together, or where we wish to strengthen a timber, for example to resist excessive bending.
In many respects, steel can be a very flexible and a very effective repair material for timber framing. Used as a surface material or indeed dropped into slots, steel is largely reversible, leaving very, very little impact on the material. It's relatively easy to calculate and indeed to see the results to make sure that what you're doing is effective if we're talking about structural failure here. And in many ways, although people think of timber as being the most traditional method of repair, actually putting a steel strap across some timbers is probably the most single traditional method of repairing timber frame buildings.
Resin repairs are often used to repair beam ends built into damp walls where the timber's in a vulnerable situation.
Bulk resin repairs have in the past been used to replace missing sections of timber or rotten joints. Nowadays, there are concerns that the hard resin can restrict the natural movement of the frame. Bulk resin repairs are also expensive.
The use of resins, epoxy resins primarily, in the repair of timber frames is a very contentious issue. And when people talk about resin repairs, they're tending to think of using the resin, I think, as a bulk material, of literally pouring the resin in as a replacement for timber. What we do is use epoxy resin as a gap-filling adhesive, enabling us to use oak as the primary repair material, but epoxy resin as the bonding material. What this has done is allow us to develop a number of more or less new ways of repairing, which can be done if you rely on the adhesive, but can't be done if you rely on what you might call traditional carpentry, jointing or bolting methods.
In practice, a combination of timber and steel repairs are the most common. This method also uses resin. Decayed timber is replaced with new timber. Steel bars set in epoxy resin provide the mechanical connection between the new and the old. This timber resin splice system is relatively new. This listed 18th century barn near Silchester had deteriorated to the point where major intervention was required. The work was undertaken by Henry Russell, a carpenter and conservator.
This particular side of the barn had actually sunk by 2 foot or maybe 2.5 foot. And it's all the studs and these two big posts had all sunk in the ground. They were just sitting in mud 2 foot down. So that meant that the whole structure was leaning down at sort of a raking angle. All the braces on this side had fallen out. And most of the bottoms of these studs were rotten. The process of actually realigning a building like this is actually not as complex as it sounds. I did it almost on my own, using acro props under the tie beams and the wall plates. You have to have quite a large number of them, and you just gradually tweak it up, and you end up with the posts and all the whole wall hanging in mid-air. In this case, because the building is covered in weatherboarding, there's not actually that much problem. You haven't got any infill panels that you've got to worry about. What you do have to worry about is whether joints like this are going to fail when you lift things up. So what I do is I fix bits of batten across, just very simply with tacks. Once the wall is hanging in the air, there was then the job of digging out the footings, which in this case I put a new concrete strip footing.
A plinth wall was built on the footing and a new sole plate was set onto the completed plinth. The studs were cut back to sound material and jointed to new sections of timber using a bolted scarf joint. This section has a tenon cut at the end so it can be jointed into a mortise in the new sole plate. The rotten end of the post was repaired using a different timber repair technique. Here the post is repaired using a 90-degree cut, thus less timber is cut away. The new and the old are located with an additional timber known as a slip tenon. The whole assembly is also bolted. Clark's Cottage, a late medieval building, was derelict for a number of years. It would have been easy to justify extensive replacement of rotten timbers, but the new owners wanted to conserve as much historic fabric as possible. This led to some interesting and quite unusual repairs.
Here we are inside what was the open hall at Clark's Cottage, and you can see that there's soot-blackened timbers here, which were originally in a room that had no chimney, far wafting up into the roof space. They're quite spindly and they're made of elm, and you can see, in fact, the original trusses fractured here. And really, there's very little way of making this structurally sound, this material, without either replacing it or splinting it with steel, or what we've done, which is actually to hold this whole truss off a new roof which is above. And you'll see here a small steel plate running through down into this timber. There's one a bit higher up, and they basically support this old truss, and in a very sort of low impact way, so that the truss no longer really takes the load of the roof. Where we've put new timbers in, we've hand converted them, and you can see that they're not soot blackened, but by hand converting we're hoping that they sort of fit in better with the original material.
The intentions behind this repair are relatively simple. A new roof structure, supported by a laminated softwood beam fixed to both gable ends, provides support for the original elm trusses. The trusses themselves are suspended from this new roof structure by specially fabricated steel brackets.
The point of showing you these repairs is to make the fundamental point that one doesn't have to make the building or the timber frame structurally sound again. I mean, this would take a lot to make this structure work again, and instead we're holding it up. And it's treating the building with respect and treating it as if it was a person. An old person may need a Zimmer frame to support themselves, and an old building equally may need some sort of structural Zimmer, and this is a good example of that.
The Wool Barn at Frampton-on-Severn near Gloucester is listed Grade 1 and was built in the mid-16th century. The date of the timber frame was established through dendrochronology. This works on the basis that the width of each annual growth ring is a record of the growing conditions in that year. The widths and pattern of the rings create a unique profile of the tree's growth. By comparing samples with a library of growth ring profiles, the age of the tree can be established. Because timbers are usually used within 12 months of felling, dating the building is fairly accurate. There had been a number of holding repairs undertaken to avoid collapse caused by a subsiding plinth wall. In addition to rebuilding the wall, the timber frame and infill panels in this area required extensive replacement or repair. A number of previous repairs were also causing problems, such as where brickwork panels had replaced rotten timbers. The roof structure of the barn comprises a series of oak trusses. The truss ties the wall frames together and supports a number of purlins running the length of the barn. Curved wind braces provide rigidity to the structure. The purlins support common rafters, which in turn support the tiling battens. A number of the roof timbers had rotted because of roof leaks. Some repairs had been undertaken in the 1940s. Part of the roof was relaid with clay tiles, and all the oak common rafters were replaced with softwood. The scale of work to the roof structure meant that all the roof coverings had to be stripped off. The clay tiles were discarded, but where possible, the slates were cleaned up and set aside for reuse. In the main roof structure, the trusses were patch repaired, but some purlins and curved wind braces were completely renewed. Traditional carpentry joints were used throughout. This is a pegged lap joint. Although a number of the 1940s softwood rafters were in sound condition, stripping the roof provided an opportunity to replace them all with new oak rafters. One side of the barn, originally a mixture of stone slates and clay tiles, was recovered with new stone slates. The overall conservation strategy was to save as much historic material as possible. However, the decision to discard serviceable clay tiles and softwood rafters can't be regarded as minimal intervention. Additionally, the principle of conserving like for like has been ignored. The justification here was that the new materials are actually the same as the original ones when the barn was first built. Their use enabled the architectural coherence of the building to be restored. The original stone plinth wall had settled over the years. The soil here, close to the River Severn, is quite soft. Distortion of the frame was inevitable. In some places, the existing wall was underpinned with concrete. In other places, where the wall was damaged, it was dismantled and rebuilt on a new strip foundation. Recording and numbering every stone was an expensive and slow operation, but it enabled the masons to recreate the appearance of the original wall. Decay of the joints in timber frames is particularly serious as the structural integrity of the whole building can be put at risk. On the gable ends, for example, some of the external cheeks of the mortices were weakened through decay. Renewing the rotten timbers would have required dismantling parts of the frame and, of course, loss of historic material. The careful use of patch repairs avoids this, and also means that the surrounding infill panels don't have to be disturbed. In a patch repair, decayed wood is cut back to sound material, and a new facing of timber is applied. These are nearly always glued and screwed to the original. For these surface repairs, where relatively thin pieces of timber are being added, the new wood should be seasoned. Ideally, the moisture content of the new should match the existing. This minimises differential movement. In some places, however, the decay was so extensive that a decision was made to renew whole timbers. The barn was originally built with unseasoned or green timber. This was felled when required, and if used green, was easy to cut and shape. Over the years, the timber slowly seasoned, hardened, and the frames settled into shape. However, the replacement timbers were from recently felled trees because in practice, ready seasoned large section hardwoods are not available. Existing timbers, in sound condition, were reintegrated into the new framing at their original location. Where possible, the wattle and daub infill panels were repaired rather than renewed. However, in some areas, the panels, despite their sound condition, were lost because the surrounding frame had been dismantled. In the past, some of the panel finishes had been renewed with hard, unforgiving cement-based render. Unlike lime render, this impedes the escape of moisture from the panel, encouraging decay in surrounding timbers. Cement render is also brittle and cannot cope with minor frame movement. When the brickwork panels were added, sometime during the 19th century, the rotten sole plate was cut out. The brickwork was dismantled and reinstated, but now on a new sole plate. Riven or split timber would have been the original material for the wattle. Splitting rather than sawing retains the long timber grains and maintains maximum strength. It also produces an undulating surface, a good key for the render. The wool barn is almost complete. The repairs have conserved an important part of the local and national heritage. The project has interpreted and applied a number of conservation principles. The success of the project can be judged in a number of ways. However, there are two key issues. Firstly, were the conservation decisions appropriate in this instance? Secondly, will the building still be around in 100 years, continuing to tell its story?